Okay, so welcome to the third installment of 4820. There's going to be more common Lisp today. That's still all we'll be talking about for this lecture. Hopefully we'll be able to cover almost everything, at least that we want to say about common Lisp for now in this lecture. But we'll certainly get back to various aspects of common Lisp in later lectures as well. But from the next lecture on, sort of the main focus will be on other theoretical concepts rather than our implementation language. Okay, so for just to quickly recap from the previous lecture, there we spent most of our time introducing sort of the most fundamental basics of common Lisp. We looked at symbolic expressions, or S expressions, and how they're built up. So we looked at atomic expressions like numbers and strings and symbols and so on. And then we looked at sort of compound symbolic expressions that are built up as lists, as these parenthetical lists that can again be nested and contain other lists. And we looked at how to define our own functions using the fun, and how to introduce variables using def parameter. And then we looked a bit at a few sort of basic patterns for how to write recursive procedures. So ordinary recursion and also tail recursion as a special case of recursion. And we also spent some time talking about this special form called quotes, which allowed us to make expressions self-evaluating. Or it allowed us to tell Lisp to basically not evaluate that expression if it's quoted. Finally, we looked at a few different sort of built-in operators for doing list processing. Something's making a humming sound from my desk. Not sure what. Can you guys hear it? Or is it just me? You guys can hear it as well. So it doesn't look like there's much I can do about that. Let's hope it just goes away by itself. Some electrical noise. Okay, let's just try to ignore it and see if it disappears. So for today, more common Lisp. We're going to be talking about some of the stuff that I didn't have time to talk about the last time, namely higher order functions. So functions that take other functions as input arguments or have other functions as their return values. And we'll be looking at sort of an alternative to recursion as a control structure in our functions. So various built-in constructs for doing iteration. We'll spend most of our time talking about a special form called loop, but also do and do times and do lists and others. And then finally, I wanted to talk a bit about other data structures besides lists, or besides sort of basic lists, such as something called property lists and association lists, and also arrays and hash tables and others. But we'll see if we actually get time to talk about that. It's included in the lecture notes, but it's something that is maybe actually more suited for self-study than for me to stand here and talk about. But reading up on what the lecture notes, there the noise disappeared. That felt good. What the lecture notes has to say about these other data structures will be important for the current obligatory assignment. So you should definitely look at that regardless, but we'll see if we find the time to look at it jointly today. Okay, so let's just get started with higher order functions first. So as I said, a higher order function is a function that either takes another function as an argument, or it has another function as its return value. So this is sort of a central concept in the paradigm of functional programming. And it's related to what I said last time about how functions are so-called first-class objects in Lisp, meaning that we can treat functions just like any other data type in our language. We can store them in data structures, or we can pass them around as arguments to our functions or as return values. So I thought we'd jointly just look at one sort of fairly typical example of a higher order function and how it works. In this example, we'll also illustrate several other concepts as well, as sort of a standard pattern for how to do list recursion, how to work with the conditional structure cond, and various other things. So here we define a function called filter, and we see it takes 2 arguments, where the second argument is actually meant to be a function or a predicate. If you remember, a predicate is a function that just returns true or false, or more specifically nil if it's false, or anything else if it's anything else counts as true. So a predicate is a function that we use to test something, to test whether some property holds or not. Before we sort of walk through the function body here and looks at what it actually does, let's look at a couple of call examples just to get a sense of what it's supposed to do. So filter will take a list as input together with some predicate, and then applies the predicate to each element of the list in turn, and then returns a fresh list to us only consisting of those elements that actually pass the test. Only those elements from the original list for which the predicate returned true. So in the first case, we send in the built-in predicate even p. So there's a convention in Common Lisp that predicates end with a p. So p for predicate. So even p will test if the argument is an even number. Odd p will return true if the argument is a odd number. Okay, so let's walk through the definition of filter and see if we can make sense of it. So we start at the top. So we use the fun to define our procedure, and it takes 2 arguments, a list and a predicate. Okay, and then we enter a cond expression. If you remember from last time, cond takes sort of any given number of test expressions, and then for the first test that is true, that sort of aborts any further evaluation of the cond expression, and then just evaluates the next expression after the test here. Okay, so we first check whether our given list is null, whether it's the empty list. If it is, then we don't do anything more, we just return nil. So we return the empty list. So remember, what we want to do here is to build up recursively a new list. And if you remember when we looked at the structure of lists in the previous lecture, sort of the basic element in a list is nil, the empty list. So in our base case here, we just return nil. If that test isn't true, if the list isn't null, we go on to the next test in the cond expression. And here we actually call this predicate that we've been given as an argument, and we call that predicate on the first argument in on the first element in the list that we're given. So that's the fun call expression here. So we use fun call to call the predicate on that first element. And if that test fires, if that's true, then you see we have a const expression, because that means we want to keep that first element in the list. So we use const because we want to build up a new list. So we const that first element of the list onto the result of recursively calling filter again with the same predicate and with the rest of the list. If the predicate turns out to not return true for the first element in the list, then we go to the final sort of default case in our cond expression, where t, the constant for the Boolean value true in Lisp, is given as the test, so that will always fire. And then you see we just recursively call filter again on the rest of the list, but without using const, without keeping whatever is the first element in the list at this point. Okay, was that mostly clear so far? Yeah. So there are actually built-in a built-in function to do the same called remove, or remove if, more precisely. But this is just to illustrate sort of how we can define our own higher order functions, how we can use fun call to actually apply a given function within the function body. It illustrates sort of several aspects of how of the typical pattern for how to do list recursion, both how to recurse down a given list argument and how to recursively build up a new list with cons and with this null test as our base case to terminate the recursion. Okay, so that's an example of how we can use other functions as input arguments, but as we talked about, higher order functions also allows us to return functions. So we'll get to that in a moment, but first we'll introduce the notion of anonymous functions, or what we call lambda expressions in Common Lisp. Again, something that is familiar to those of you who've taken the scheme course previously. Okay, so in Lisp we can create functions without actually giving them a name. So we can define a function without using this defun construct. And we do that using something called a lambda expression. And you see sort of the general form here of a lambda expression. It takes a parameter list, just like function definitions using defun, and it takes a body. So the only example is that we write lambda instead of defun, and we omit the name part. We omit the variable that we otherwise bind the function definition to. So creating anonymous functions are typically useful when creating functions on the fly, for example. So here we see an example with the filter function, the higher order function we defined on the previous slide, where instead of passing in sort of an existing named procedure, we just pass in a lambda expression here instead. So this would be this lambda expression would correspond to a function that expects one argument, x, and we see that the body of the lambda expression is just an AND expression. So AND is something I guess was on the lecture notes for the previous lecture, but maybe one of the things we didn't actually have time to talk about. So but I think you'll all sort of understand the interpretation of logical AND from other programming languages that you had. So it AND will basically check whether each of the expressions given as its arguments are true. If all of them are true, it will return the value of the final expression. If not, it will, if it finds an expression that is not true, it will immediately abort any further evaluation and return nil. Okay, so in this case, our anonymous function, our lambda expression, checks whether its argument, the x argument here, is within some given interval, whether it's larger than 20 or whether it's smaller than 50. But imagine now, just for the sake of the argument, that this is something we find that we want to do often. So maybe in our application we find that very often we want to sort of on the fly dynamically create tests that allow us to check whether a given argument is within some given range or within some given interval. So then maybe it would be useful for us to have some procedure that allows us to actually more compactly sort of create these tests for us. So that's what we'll be doing here. We'll be defining a procedure called create range test that takes two arguments, defining the lower and the upper bound of the interval that we want to check if something falls within, and return a new predicate for us that that does that check. That checks whether a number is within that interval. And given what we now know about anonymous procedures or lambda expressions, it's very easy to write a function that actually returns another function, because all it needs to do is return a lambda expression. So in this case, create range test takes 2 arguments, so lower, upper, and then we see that in the function body, everything it does is actually just to immediately return a lambda expression. It doesn't do anything else, it just returns a lambda. So it returns a new procedure, which is very much similar to the one you saw on the previous slide. A single argument procedure that checks whether the argument is within the range given by lower and upper. So let's use that again with this filter procedure that we defined initially. So now we can, so first here we create a variable called foo bound to a list. Should be an additional closing parenthesis here after the def parameter expression. Then we call filter on this list where the predicate argument that we send in this time is one that we here create while calling filter. We call range test with 10 and 30. So the result now is a list that contains only 11 and 22, the only elements of that of the list foo that would return true for this predicate that we just created here. If we call create range tests with other arguments, we get another return value for a call to that same filter function. Some of you, even if you haven't taken the 2810 functional programming course before, many of you will probably have seen lambda expressions and worked with higher order functions in other languages, in like Python, for example, that also has support for this. Okay, so that's basically what I wanted to say about higher order functions, and then I wanted to talk a bit more about some other details related to how we can details related to defining our own functions. Namely, some aspects related to how we can flexibly use parameter lists in Lisp. So first we'll look at how we can define optional parameters, how we can define a function to have possibly 0 or more required arguments, but also any given number of optional arguments that we can choose whether or not we wanna pass in. So in this example, we define a procedure foo that has 1 required argument, x, and 2 optional arguments, y and z. And any optional argument that is not actually provided when we call foo, in this case, will be initialized to nil. That's the default. But if we include, like you see for set here, we in the parenthetical here include a default value, in this case 42. So if we don't supply a value for the set argument, that will be initialized to 42. So in the function body here, all it does, for the sake of the example, is just to return a list of the 3 arguments that it can take, x, y, z. So see if we call foo on 1, it returns the list 1, nil, and 42. So 1 is the value we passed in, and the others are the default values. If you call foo with 1, 2, 3, so here we actually provide a value for these optional arguments y and z, then those are used instead. Alternatively, we can also make such optional parameters named using what we call keyword arguments. So for optional arguments, we use this sort of syntactical keyword here, ampersand optional. For keyword parameters, we use ampersand key in the parameter lists. So in this case, the y and z are still optional, and they have the same default values, nil or 42. But in the second calling example here, we see that we can now, when we call foo, we can refer to these parameters by their names, by the names that we have given to them in the parameter list. So here we say that set should have the value 3, and the parameter y should have the value 2. And notice that that means that we don't have to worry about the order of the arguments. So they don't have to be provided in the order that they're given in the parameter list. We're now free to give them in any order we want because they're named. This is also nice if you have procedures with sort of long lists of possible parameters, because it makes the code more readable. So rather than having to map sort of the 10th parameter position when calling this function, what does that actually map to in the function definition if we're trying to read the actual code. If you have keyword arguments and we use sort of sensible meaningful names for the parameters rather than y and z that we're using in this case, which doesn't offer much help because it's a nonsensical procedure to begin with. But then we can refer to the arguments by their names, and makes the code more readable. Yeah, question? If you move the set you meant to the left, so then it would no longer be an optional argument. Then it would be a required argument. And then it wouldn't make sense to give it a default because it would be required. But so if you moved set to the left-hand side of the optional marker here, that would mean saying that set always had to be provided when you call the function, and then it wouldn't make sense logically to provide a default even, because that default would never be used because you would have to supply a value. So yeah, the answer is no. You can't just move set to the left here. Okay, finally, one more variant of how we can define sort of optional parameters is to use a keyword called rest. So with this rest marker in the parameter list, it means that anything follows that. That can be an arbitrary number of arguments. It can be 0, or it can be 1,000 more arguments that we pass in. But regardless, all of them will be gathered up in a list. That that list will be given whatever name we insert here. So here we've used rest for the parameter name itself as well, which is fairly typical to do. So the idea here is to define a function that will compute the average of whatever numbers it's given, and it requires minimally one argument, but then it will also happily accept any other number of arguments. So we'll go through the function body, but first you can see the calling examples here. So if we call it on average on 3, it returns 3. If we call it on 7 arguments, it returns the average of that. So let's see what's going on in the function body here. So we see that we have a let expression for introducing a local variable, numbers, and we bind that to the result of simply consing x onto this list of whatever other arguments are given in. So like in the first calling example here, rest will be nil. It will be an empty list because we didn't supply any additional parameters. In the second calling example, rest here would be the list consisting of 2, 3, 4, 5, 6, 7. And we cons 1 onto that to make sure everything is in one list. And then we use apply to call the plus function to that list of arguments. So we here have to use apply rather than fun call. And the reason is that we now have a list of arguments. Plus doesn't take a list as its argument. Plus can take any number of numeric values as its arguments. But here, the numbers are already in a list. So we use apply, which is a way to apply a procedure to a list of arguments. And then we compute the length of the argument list and divide the sum by that. So the reason we use a let construction here to introduce temporary variable numbers is just so we don't have to do this consing twice, because we use numbers as the argument for both apply and for length. So let is also one of the things we looked at in the previous lecture. Okay, so that's it for what I wanted to add from the last time about various other aspects related to defining our own functions. And not only for defining our own functions, because I mean several of the built-in functions in Common Lisp also make use of this. So plus, for example, takes optional arguments. Several of the built-in functions in Common Lisp take keyword parameters, named parameters, like here. Okay, but now I wanted to turn to something different. We will end up talking about iteration now, but first I wanted to mention quickly the notion of macros in Common Lisp. So one nice thing with Common Lisp is this uniformity that, as you've seen, Lisp code is actually expressed using a Lisp data structure, namely lists. And that makes it very easy in Lisp to write code that actually manipulates code. Not everything looks like lists. We have all these parentheses. Is maybe what makes Lisp sometimes look weird immediately to someone who's new to Lisp. But for a seasoned Lisper, that's sort of part of the beauty of Lisp, that it's that there's hardly any syntax at all. You have this nice uniformity that everything follows. And the most powerful way in Common Lisp to have code that sort of manipulates code is given by the macro system. So the typical sort of slogan or pitch when introducing macros is to say that there are programs that themselves generate programs. And what macros do is they provide a way for us to take the code before it's passed to the compiler and manipulate it and rewrite it. And this basically gives us an easy way to extend the language. Not only extend it with adding additional function definitions, but extending actually the syntax of the language. And we've already seen several built-in Common Lisp macros, like and or if, cond, defun, setf, and so on. So what we refer to as special forms. Constructions in the language that don't follow sort of the standard rule for evaluation. So what a special form or a syntax macro allows us to do is to control when or if at all a given argument is to be evaluated. And although we won't actually be looking at how to write our own macros in this course, for those who are sort of interested, it's possible to read up on that in the practical Lisp book. But it's sort of out of scope to cover in this course. But we'll be looking at some examples that illustrate very sort of nicely to what degree macros can be used to redefine the syntax of the language. And the best such example is loop, or possibly the worst such example, depending on who you ask. Okay, so before we look into the details of loop, just want to mention a note about iteration. So far we've looked at recursion and various ways to do recursion, such as this special case of tail recursion that we talked about last time. And although recursion is powerful, it's sometimes more natural to express something using iteration. And Common Lisp, as opposed to Scheme, comes with several sort of built-in constructs for doing iteration. There's one called do, which I won't cover here, but that you can look up yourself if you want to. But there's two simple ones called do list and do times. We'll look at those two in turn before we look at loop. So do list takes a list and introduces a variable, in this case x, that will be successively bound to each element in that list. So in the body of do list here, we do whatever we want to this x variable and then move on to the next element in the list. So in this particular example, we have the do list within a let expression where we've introduced a variable called evens that we've initialized to the empty list, nil. And then we want to create a list of the even numbers that exist within this list of numbers. So we use when. That's also another conditional structure that we haven't looked at before. So in addition to cond and if, there's when and unless. And when basically does what you'd expect it to do. It takes a test. If that test fires, it does whatever is in the body. So in this case, if x is bound to an even number, we push x onto the list evens. If you remember from last time, we talked about setf, this sort of universal assignment operator in Common Lisp. We also looked at various sort of specializations of setf that are built on top of setf. And push is one such example. So push will destructively add x onto the list evens in this case. So push destructively adds an element to a list. And once we've gotten to the end of the list, x has been bound to all elements in the list, and we exit the do list expression, we return the result of reversing this list of even numbers that we've built up. Okay, let's look at an example using do times. So do times is similar to do list, except that it just binds the variable to the successive numbers from 0 up to whatever number we specify, in this case 6. But the rest of the expression here is like what we just saw. Okay, so that's fine, but now let's see how we can do that using loop, which is basically a much more powerful and general and versatile construction than these other iteration constructions. So loop here basically tells us to bind x to all numbers below 6, and whenever 6 is an even number, collect it. And then in the end it will return the list that it has created using collect. So we immediately see here that this doesn't really look that much like Lisp. So sure, do list and do times, they are both themselves special forms defined as macros with their own sort of peculiar semantics in terms of how they introduce this local variable x and bind that to successive values across the list in the case of do list, for example. But still, it more or less looks like Lisp code still, at least if you go by the number of parentheses, right? But for loop, things look a bit different. So loop is a macro that was designed for expressing iteration in a way that is as close as possible to natural language, basically. So you can almost just read out the code aloud, and it almost sounds like a sentence, right? It sounds like a statement about what the loop is supposed to do. And it has all these specialized syntactic keywords like for and below and when and collect. So in many ways, loop can be viewed as almost a mini language, a sub-language within Lisp for expressing iteration. we'll look at some other examples. So in this case, we introduce a variable I that will be bound first to 10, and then by steps of 10 up to 50, and then we collect them. When the loop exits, it returns the list that it has built up using collects. So we'll see there are also other sort of, accumulator keywords besides collect that we use in this case. So we could have had sum, for example, or minimize or maximize if you wanted to just look for the minimum or maximum value of something. We could have used append if you want to append together lists, and there are many other accumulators that we can insert here. But so loop at least serves as a good example of this power of macros for extending the syntax of our language. Because we couldn't have written something like loop using just the fun. We couldn't have implemented loop just as a procedure, because its syntax goes beyond what is standard for the language. As I said, so loop is very powerful, very general and usable, but it comes at this expense of breaking this nice property of uniformity that we have otherwise in Lisp. So it has a different syntax, and you need to know the meaning of all these special keywords in order to be able to properly interpret what's going on. Paul Graham, who I also mentioned in the previous lecture, one of the sort of gurus within the Common Lisp community, has written several great books on Lisp, called loop one of the worst flaws in Common Lisp. That's basically exactly because of this thing that I just mentioned, that it breaks this nice property of uniformity. So yeah, many people have strong feelings about loop. Some people don't like it because it's non-Lispy, but still, it's no denying it's a very powerful construction for expressing iteration, and something you're encouraged to use as well. A couple of more examples before we'll take a break. A couple of more loop examples. So in this case, we've introduced a conditional in the loop, so we can have things like when or if inside the loop. So in this case, I will be initialized to all numbers from 0 up to 10, and whenever we find an odd number, we ask loop to sum that for us, and that sum is what is returned. So the sum of all odd numbers below 10. If we have vectors or strings, so we've seen strings so far, but haven't really talked about how that is implemented, or the data type of vectors, which foo is a subtype of. We'll get to that later today. If you want to use loop to iterate across the elements of a vector, or in this case a string, we use a cross. And again, we collect that into a list using collect. So the element in a string will be the characters, which are expressed like this in Lisp. The hash and slash. Okay, here's another example of loop. So here we have an example of introducing a local variable in the loop. So we use with for that. So with introduces a local variable foo that will be bound to a list in this case, and will not be updated in each sort of step in the iteration. We just introduce that at the beginning when we enter the loop. And in this case, we actually have another variable I that we use for iterating through the elements in this list foo. And we also have another iteration variable j, which basically just counts up from 0 until we reach some stopping criterion, and then we print in each iteration this print statement. So format is also something we haven't looked at yet, but which we'll get to in a couple of slides. But I think so there are a few more loop examples. I think you can just look at those for yourselves. They're in the lecture notes. I think that's probably more suited for you to just study on your own. And we also include basically sort of a mini reference for all the different keywords that can be used when writing a loop expression. Yeah. Yep. Yeah, so everything marked in red here is just to highlight what are these sort of syntactical keywords of the loop. Here it is. Yes, there is actually also a return loop sort of syntactic keyword, but the return here is just standard the return function of standard Common Lisp. But yeah, so this is also this overview of the various keywords that you can use is basically for you to have as a reference, and not something I'll be going through in detail in class. But just note that there are sort of a bunch of different ways to do accumulation. I mean, to count things, to sum things, find the minimum of something, or collect or append things into lists. Various conditional control mechanisms like while and unless, and so on. And you can also do iteration over basically any data type. You can do loop iteration over hash tables, or over vectors, or strings, or lists, or over just numeric ranges. So it's very versatile. Okay, that was all I wanted to say about loop. There's also some loop expressions that are part of the sort of pre-code that you've been given as part of the first obligatory assignment. So already there, you'll be required to try to make sense of how loop works. Okay, let's pick up again in 15 minutes. Okay, so we had just finished up our quick tour of iteration in Lisp with loop. Now just a quick notes about some various sort of bits and pieces that we haven't sort of managed to fit in other places. First, just a quick note about reading and writing in Lisp, input and output. So we do that using streams, and format is what we use for printing things. And the first argument here is the stream, but if it's just says T, then that indicates the default stream, typically the terminal. And the rest is a format directive, where we have these placeholders here, giving us the tilde ace, and the arguments given after the format directive here will be sort of plugged into these placeholders. So again, format is an example of a fairly extensive macro that almost defines a mini language within this, just like loop does. So for format as well, there's a bunch of different keywords and directives you can use for specialized printing of different data structures, or you can even do simple iteration within the format directive that you supply. Quite often when I find myself looking things up in the hyperspec, so what I mentioned is this standard reference place to go to if you want to look up something about Lisp, or if there's a Lisp function that you're wondering how it works, then go to the hyperspec. We we're linking to that reference resource on the course webpage. And very often when I find myself looking things up in the hyperspec, it's to find out how I'm supposed to do something using formats, because it's easy to forget all the specialized ways of using formats to print. For reading, there are basically two functions. There's readline, which will read in one line of text at a time from a given stream, and returning that as a string. So in the obligatory exercise that you've been given, there's an example there of using readline in the pre-code. And there's also another more sort of Lisp specialized variant just called read, which actually expects to read in symbolic expressions, S expressions. So read will read in one well-formed S expression at a time. So that's useful for reading in Lisp code or Lisp data structures. Some of you might have noticed the nil here as the second argument to both readline and read. That just asks Lisp to return nil when encountering the end of file. So here's just an example in use, similar to what you're seeing in the pre-code for the obligatory exercise. So here we use the with open file special form to create a stream bound to the stream variable here. We open a file called sample text and specify that it's for reading in rather than printing. Then you see an example of loop here for iterating through that stream, reading in one line at a time. So line here will successfully be bound to a string corresponding to each line of the input stream, and then we use format to basically print out whatever was in that file. Okay. Again, something which was actually part of the lecture notes for the previous lecture, but that we didn't have time to look at. Hence it says recap. But it's not really a recap since we haven't actually looked at this at all so far. We have talked about predicates in general. So a predicate is any procedure that tests whether some property holds or not for the argument or the arguments and returns true or false. And there are a plethora of built-in existing predicates for specifically testing whether or not two arguments are equal in some sense in Lisp. Various perspectives on what it means for something to be the same or to be identical. And in particular we have these four: EQ, EQL, equal, and equal P. And we'll talk about the difference of these four. So EQ is sort of the strictest of these procedures, and tests basically whether two objects are refers to the identical place in memory, whether two objects are identical. So EQ is what we want to use if we want to test exactly whether two objects are identical, really the same. It will also it also happens to be well defined for symbols, since just as a matter of fact, symbols are unique in Lisp. So if you can use EQ to test two quoted symbols, and that will return true. But for other types like numbers or characters, EQ will not be useful for finding out whether or not they're equal, unless they refer to the same object in memory. EQL is like EQ, but it's also well defined for numbers and for characters. And equal is even more general and also tests recursively the structural equivalence of lists. So you can test nested lists even, and if they contain the same values, although they're separate lists, separate sort of objects in memory, equal will return true. Equal P is even more sort of admissive and will return true regardless of the case and the numeric type of the argument. So we'll look at a couple of examples. So here we use EQ to compare two quoted lists. So two lists of 3 elements, 1, 2, 3. But since each of these lists will be distinct objects in physical memory, EQ returns nil. They're not the same identical objects. If we use equal on these same list arguments, it returns true, because it doesn't care that they're not the same objects in memory. It just checks whether the values in those two list structures are the same. If we try to call EQ onto numerical values, you may or may not get true as your answer. That's left to the specific implementation. So that's undefined according to the standard. It's not specified. If you use EQL to compare two numbers, on the other hand, like in this case, 42 and 42, we're guaranteed to get true. EQL is well defined for numerical values, but it does not take into account numeric type. So if you want to disregard numeric type, we use equal P instead. For comparing strings, we can use equal, like we did for our lists. But if we have strings with different case, we would need to use equal P if you wanted to have all caps foo and lowercase foo to be the same. Okay, so why do we have all these different built-in equality predicates? It's basically because it's the more specific test you use, the more efficient it is. So using equal P, if you know that EQL is sort of sufficient, then it's better to use just EQL. And if what we wanted to check is really whether or not two objects are actually the same object in memory, then we'd want to use EQ. So they work for sort of different circumstances depending on what we want to do. If you think it's confusing and you find that you're often unsure of which one to use, one strategy could be to use only EQ if what you want to test is exactly sort of object identity. In all other cases, you could go for equal or equal P, and then you wouldn't have to think about what these other guys mean. So in addition to these, there are also many specialized equality predicates for different types. For numerical values or for strings, etc. But these are more general. Okay, so the last sort of big chunk of things that I wanted to talk about today are data structures. But I don't think all of that is necessarily so important for us to cover jointly. So we'll see what we find time for in the end. Some of it I think might be just as well suited for you to look at on your own. So before we turn to data structures, I thought we'd do a quick quiz using Kahoot. Some of you might have used that before. So hopefully as many as possible of you have some mobile unit with you that runs the browser, because you'll need a browser to participate in the quiz, either a smartphone or a laptop or a tablet or whatever. And I suggest that everyone will pair up with whoever is immediately to the right of them, so that you solve the quiz in pairs 2 and 2. If you don't have anyone immediately to the right of you, then go to the row in front of you. If you prefer to do the quiz on your own, that's fine. If things don't really sum up and you want to be 3 instead of 2, that can work as well. Up to you. And if you don't have a unit running a browser at all, you can also still do the quiz on paper, but you just wouldn't be able to see your votes on the screen. But you can still try to solve the quiz. Okay, I think I'll turn off the screencast because that will just be annoying. But we'll, for those of you who are seeing this later on the screencast, we'll post the link to this Kahoot quiz on the course page later, so you'll be able to sort of rerun it later or do it on your own. That was our quiz. Let's go back to where we left off. Okay, so data structures is what we wanted to turn to. So we won't have time to go through all of them, but let's at least spend some time on some of them, especially this first one will be interesting to note, namely arrays. So arrays in Lisp can be created using a constructor called makeArray. It takes the dimensionality of the array, the length or the number of elements as arguments. And if you don't supply an initial value, the elements will default to nil. We can use aref to pick out elements from an array referring to their index. So arrays are basically an integer indexed container structure, counting from 0. We can use setf, this universal sort of general assignment operator that we've seen several times now. We can use that on aref to change the values stored on a given index in an array. So in this case, we say that the first element in the array with index 0 should have the value 42. So if you now write array on the REPL, we see that the first element is now 42. So Lisp arrays can be fixed sized, so have a given fixed length, that's the default, or they can be made to be adjustable, so that we can dynamically actually ask for the array to be extended. A peculiar thing of Lisp arrays is that they can also be used to represent grid structures. They can be multi-dimensional. So in this case, we've changed the first argument to the makeArray constructor to be a list of numbers, where each number refers to the number of elements in that corresponding dimension, if you will. So this would create a 2x5 array with all elements initialized to 0. So here we see an example of these keyword arguments that we talked about in use, named arguments. Yep. What does the hash mean now? Yes. Notation. So should I mention that? The hash here is basically just the Lisp convention for the printer for how an array is shown on the REPL. Yeah. I think the reader would actually accept you writing it directly as well. So here's another example of updating or assigning a value to an element. So if you remember, incf was one of these specializations built on top of setf. So here we say that we wanna look up the second element in the first row, basically, and set that value to be 1. So if you look at the diagram here, this is what we will look up. And since the values were initialized to 0, they're already numerical, so we can use incf to increment them by 1. Okay, there are also some other specialized versions of vectors. In particular, when we say a vector, that's just a one-dimensional array. A non-dimensional fixed size array. And strings, again, are a specialized type of vectors. There are also other specialized types of vectors like bit vectors. And to as a generalization over these various different types of vectors and also lists, there's a more abstract data type called sequence. So a sequence can be a list, or it can be a vector, it can be a string, for example, as an example of a vector. And there's a large number of built-in sequence functions that will operate on sequences, regardless of whether we give them a string as an argument or a list as an argument, for example. So we'll look at some examples. So length, for example, we've seen that applied to lists. We can also apply that to a string or another vector. Elt for element, a more general version of nth that we looked at the last time for picking out an indexed element of a list. We can use this more generally to pick out an indexed element in a sequence. Countif takes a sequence, whether it's a list or a vector, and counts the number of time a given predicate that we pass in holds. So in this time, any guesses as to what this would return? Countif with the predicate number p on the list you see here? 2? Yeah. Because this guy here, the number 2 is actually a string, so that will return false for number p. Subsec, that's also used in the pre-code you're given for the exercise. So subsec takes out a subsequence, a slice of a given sequence, corresponding to the indexes that we pass in as arguments. Substitute for doing replacement. So again, we encounter the hash notation. This time, it means something else. So this is how a character is represented in Common Lisp. So a string is basically a vector that consists of characters that are printed like this when shown individually. There's remove, sum to check whether some element satisfies a given predicate. You can do sorting, all sorts of things. And there's a bunch of other ones built in as well. Position, every, count, remove if, and a bunch of other ones. So you should at least just know that if you're looking to, so working with sequences is sort of an abstraction, but there exists very extensive support for in Common Lisp, in the Common Lisp library. The remaining slides here, I think I'll leave for you to study on your own. I'll just mention that there are several sort of built-in various data structures for key value lookup, so associative data structures, so where you have a key that's associated with some value. So at least 3, namely property lists and association lists, which are both built on lists. And then there are hash tables. So I suggest you just go through these yourselves. So reading up on association lists, for example, will be useful for one of the questions that you're asked to solve in your assignment. The same with hash tables. We'll probably return to these later once we start talking about the choice of data structures in some of the later obligatory assignments. So we'll revisit this, but for now I think I'll just leave it to you to read on your own. Structures is actually a very useful data structure that is not covered in the Seibel book, the practical Common Lisp book. So he covers the Common Lisp object system, but it does not cover what is called structs. So maybe this slide in particular, I would advise that you take a look at. We might get back to some of the other remaining remaining issues next week. But finally, just for what we'll turn to next week. So next week we'll turn to some more sort of proper content. We're done with our super quick crash course on Common Lisp. Although, as I said, we'll get back to various aspects related to Common Lisp later. But the main bulk of what we wanted to tell you about Common Lisp has been covered now. So next week we'll turn to something called vector space models and distributional semantics. So distributional semantics is a theory about word meaning, stipulating that we can infer what semantics or what meaning a given word has just by looking at its context of use. And we'll talk more about the details of what that hypothesis sort of entails next time. And then we'll introduce the notion of vector spaces, which is sort of a general framework for representing data or a particular problem based on a geometrical metaphor. And so we'll be starting out with distributional semantics for trying to automatically infer the meaning of words. Then we'll try to represent the meaning of words in a vector space model, in a mathematical geometrical model, which will allow us to reason about what words mean the same things, what words are similar, what words are dissimilar semantically, by measuring their distance in this geometrical space, in this geometrical model that we'll be constructing, which is also something you'll be implementing yourself. Okay, but that's it for today. See you in a week.